How do we add two complex numbers? What are the properties? Most of the properties of simple addition that we have learned in 6th and 7th grades, the properties of commutativity, associativity, distributivity, etc., are also applicable to complex numbers. Okay, first property. Complex number addition is commutative. So z1 plus z2 and z2 plus z1 are both the same complex number. They are associative. So if I have three numbers, at least three, and so I add the sum of z1 and z2 to z3, that gives me the same complex number as if I have added the complex numbers z2 and z3 first and added the result to the complex number z1. Okay, so that's associative property of addition of complex numbers. And then there is existence of additive identity. That is, if I have a complex number and if I add the complex number 0 to it, I'll get back the complex number z. Okay, so therefore that is the existence of additive identity. So therefore here I'm going to write not 0 plus z, 0 plus z, it's equal to z only. Existence of additive inverse. So additive inverse is the number which we add to cancel out the existing number. So z plus minus z gives us, or minus z plus z is equal to 0. This is the additive inverse of the complex number z. Okay, what next? Subtraction. If I have two complex numbers, z1 is equal to a1 plus ib1 and z2 is equal to a2 plus ib2, then z1 minus z2 is equal to a1 minus a2 plus I into b1 minus b2. Okay, so next, multiplication. If I have z1 is equal to a1 plus ib1 and z2 is equal to a2 plus ib2, then z1 times z2 is equal to a1 plus ib1 times a2 plus ib2. Now what happens here? Between these two lines, what is happening is that we have multiplied it out. So a1 times a2 plus a1 times ib2 plus ib1 times a2 plus ib1 times ib2. So a1 a2 plus I into a1 b2 plus a2 b1 plus ib1 times ib2 is I square b1 b2. I square b1 b2 is minus b1 b2. And so this is equal to a1 a2 minus b1 b2 plus I into a1 b2 plus a2 b1. And that is what has happened over there. As you can see, this is how multiplication of two vectors is done. It's slightly more complicated than simple number multiplication, but then this is how it works, right? That's because of the existence of the great iota. Okay, next. What are the properties of complex number multiplication? Z1, Z2 is equal to Z2, Z1. That is the complex number. That is, I just keep saying vector multiplication, but complex number multiplication is sort of like vector multiplication. So it is commutative. So Z1, Z2 and Z2, Z1 give us the same complex number. It's also associative. So therefore the product of Z1 and Z2 times Z3 is the same complex number as the product of Z2 and Z3 times Z1. And then there's the existence of identity, additive identity. So if I multiply by the complex number 1, some complex number z, I get z, right? And the existence of multiplicative inverse, that is, if I have a complex number z and if I multiply it by 1, that is, if I multiply it by another complex number which is the multiplicative inverse of that, I should get 1. How do I get this complex number? So this is an interesting thing in itself. If z is equal to a plus ib, then its multiplicative inverse is the complex number a minus ib. Is it? No. It's just the conjugate of this complex number. So z is equal to 1 by a plus ib. If I multiply it by a minus ib, what do I get? It is a minus ib divided by a square minus ib the whole square. Why am I doing all this? To get the multiplicative inverse, so that finally when I get z dash is equal to a by a square plus b square minus I into b by b square, a square plus b square, this z dash is the multiplicative inverse of the complex number z is equal to a plus ib. So z into z dash is what gives me 1. You can do this, you can prove yourself that this is the multiplicative inverse by actually multiplying out the two complex numbers. So z is equal to a plus ib and z dash is equal to a divided by a square plus b square minus I into b upon a square plus b square. And so we get a times a by a square plus b square minus I into ab divided by a square plus b square plus I into ab divided by a square plus b square minus I square b square divided by a square plus b square. So therefore we get a square by a square plus b square, I into ab by a square plus b square minus I into ab by a square plus b square. Both of these will get cancelled. I square is minus 1, so minus of minus 1 is plus 1 plus b square divided by a square plus b square. And so we get a square by a square plus b square plus b square divided by a square plus b square. So therefore this will be equal to a square plus b square divided by a square plus b square, and thus we get 1, which means definitely a by a square plus b square minus I into b by a square plus b square is the multiplicative inverse of z is equal to a plus ib. Okay. Division. How do we conduct division of complex numbers? So if I have a complex number z1 and I have divided by the complex number z2, then I write it as z1 by z2, which is z1 times z2 to the power of minus 1, which is equal to 1 by z2, and that has to be dealt with in a separate way. So what do? We multiply and divide it by the conjugate of the complex number z2 so that you don't have iota in the denominator. Okay, so for example, if I have z2 is equal to a2 plus I into b2, so I have z1 by z2 is equal to z1 times 1 by a2 plus I into b2. So therefore this is equal to a2 minus I times b2 divided by a2 minus I times b2. So therefore this is equal to z1 times a2 minus I b2 divided by a2 square plus b2 square. So now because of the multiplication of a2 plus ib2 with a2 minus ib2, the iota gets removed from the denominator so that we can comfortably get a complex number in the form a plus ib by multiplying out this with the complex number z1, whatever it is, so that the iota remains in the numerator and you get a neat complex number in the form a plus ib. That is what you do when you have to divide one complex number by another complex number. But mostly you won't be dealing much with problems of that type. But anyways, this is what you do in case you do encounter such division.